Hi all, this is Dr. Gopal Reddy. Our today's topic is organometallic compounds in the bonding system. That means if the metal ion make a bond with either eta 1, eta 2, eta 3 and so on, that is epicity 1, epicity 2, epicity 3 and so on. That means how many carbon
So,
atoms are coordinating to
first
the
let us
central
consider
metal
the
atom
sigma
that
bond
we are going
formation.
to
A sigma bond
study
means it
here.
is single bond formation between the central metal ion and the that of the carbon atom. See here now. So here mercury is forming sigma bond with that of the carbon atom. That is, see what I mentioned here, H1. H1 means it is epicity 1. So the bonding ability of the ligand is known as epicity. That the carbon atom is able to form a bond with that of the central metal ion, that is called as epicity. The number may be varies. This is 1, 2, 3, 4, and so on. So this can be also be denoted by, so eta, the symbol called as eta. So here H1 is given. That means that one carbon atom is coordinating the cyclopentadiene. So from this ligand, one carbon atom is coordinating. Similarly, from this ligand, that is cyclopentadiene, so one carbon atom is coordinating with the central metal atom. So that is given as H1. Similarly, so here we can be given as at H2, H4 and H6. Let us discuss here. So this the carbonyl group, CO groups are there here. There are three CO groups are there. So all are called as H1. So whereas the central nickel atom is there. So with this nickel atom, this carbonyl and this carbonyl is forming a bond with the, so one carbon atom, that is through carbon atom. So that we all know that, so that will forming what a linear geometry with this forming. So eta 1 and eta 1 are H1, H1, H1. So whereas from, if you consider the this ligand, from this ligand, so here are given as H2 or eta 2. That means there are two carbon atoms are coordinating to this nickel atom. So here one carbon atom and here one carbon atom. Similarly, if you come to the this one, it is H4. Similarly, other hand, 1, 2, 3, these three carbonyl groups, carbonyl ligands are coordinating to central atom through carbon atoms, so without forming a single bond. But here the iron, in the other hand, from this ligand, it is coordinating to two pi bonds here. That is H4, where what we mentioned here. This ligand, from this ligand, there are four carbon atoms are coordinating to the central iron atom. And similarly here it is H6. That means there are six carbon atoms are coordinating to the central chromium atom. That is two here, two here and two here. So that is whenever when you show this bond to the central sort of pi bond, that indicates that both the carbon atoms is ability to forming the bond with the central atom. So that is bonding system in the so sigma bond and the metallics. Let us consider the bonding system including the H1 ligands. Also, if we see here, this center titanium here. So this titanium, it is forming H5 here, H5 here, H1 here, H1 here. See, so you can make out a difference between these two ligands and these two ligands. So here all the ligands are same. That is cyclopentad compound. So here that is the titanium C5H54. That is this ligand, this ligand, this ligand. All the ligands are same, but the coordination with the central metal ion is different. That is, see in these two ligands, that is H1 and H1. So this central metal atom is coordinating to this ligand and this ligand through a single carbon atom. Here one carbon atom, here one carbon atom. But see the representation of these these two ligands. This is H5 and H5. That means, so if when this central metal ion atom is can be ability to coordinate with the all the five carbon atom, and here also this central atom is coordinating with all the five atom. So this is another interesting compound that shows that different bonding ability of the cyclopentadiene, that is titanium C5H5 4 time. In this compound, two of the cyclopentadienyl, that is this one and this one ions, are coordinating with the H5, these two, and other two are bound through only one carbon atom, that is called as H1. See now here these two are what H1, but these two are what H5. of the metal atom. This compound S structure. Therefore, the formula for the compound is written as H5C5 twice. That means H5, which is indicates the epticity in front of the ligand. That means this ligand, this, because we can't write the structure like this. So when we write the rotation like H pi or eta pi in front of the ligand means, from this ligand there are 5 carbon atoms are coordinating with the central metal ion. How many are there? H5, that is 5 penta epto, that is 5 carbon atoms are coordinating the central atom. That are 2 ligands are there. Similarly, H1, that is, see now here these two are H1, right? So C5 H5 twice titanium to show the different bonding modes of the cyclopentadienyl rings. So should not write. So this entire complex has titanium C5 H5 4 times, because so we can't make out the difference what kind of bonding is arise in this kind of ligands. So when we write the molecule, the structure of this molecule like this, we can make out the difference between whether it will be what so monoepto or pentaepto. Other organic ligand can also be bound in more than one way. So, which for example, allyl group can be bound to the in a sigma bond to one carbon atom is H1. See now here, see Mn and this C, right, which is coordinating with the single bond, which is given as what H1. See, because this central metal atom which can be directly coordinated with the carbon atom, that is H1 allyl group, which what we are given here, that is monoepticity. So and other as a pi donor comprising all 3 carbon atoms like H3. See now another same kind of ligand which is coordinating with this 3. So this one, this one, and this one. Mn is coordinating with this carbon atom. That is, sorry, I'm not able to mention here. So there is a dotted lines are there between these 3 carbon atoms, whereas in such ligands are can be represented as what H3. That is H3, that means there are triepticity. See now here same ligand allyl compound, same ligand allyl ligand. So here it is epticity is 1 and here epticity is 3. So that means that so there will be different bonding modes, and nature is will be there the same ligand with a different so metal ions. So this is a bonding system in alkenes. If we come to the alkenes, we can be generally we consider the ethene. So in the 1827, Danish chemist Gis obtained a new compound. He took the KCl PtCl2 ethanol from the reaction, which can form K2PtCl4 with ethanol. Only in, this can be called as what Jesus salt, which are the general formula KPtCl3 C2H4, so H2O containing coordinate with the ethylene, which can be formed by a dehydration of the ethanol and water crystallization. The metal is bound to the both carbon of the ethylene. See now this is a platinum metal is there. So this platinum metal which is can be bound to the this carbon as well as this carbon of the ethylene group. See this is ethylene group. So in this ethylene group, the central metal ion can be bound to the this carbon and this carbon as well. This allows the metal to bind efficiently to the pi electrons of the alkene. So whereas when this central metal ion can be coordinating with this carbon and this carbon as well, which will be form most strong affinity with the central metal ion. For this salt, the best bonding is given by a Dewar chart model. So this was explained by what this model, because these hydrogen and this hydrogen, this hydrogen, this hydrogen will be try to present away from what central metal ion. This involves the donation of the carbon-carbon pi electron to an empty d sigma orbital of the metal. So this electron pair now delocalize over the 3 centers, metal, carbon, and carbon center. So now here, so this will be helps to water. So this will be try to present away, and what happen when this bond will be making to bond present with making bond with this pi bond by electrons, and this will be become what bond will become what weaker, because when the central metal atom will be goes to the back donation, so that kind of back donation we are observed in the so carbonyl compounds. So similarly, what happens first, the carbonyl compound will be donate the electron density to the central metal ion. So when the central metal ion will be gaining become electron rich, so then what happened, to make electron neutral, the metal atom is start giving the electron density towards back to ligand. At that time the electron will be go and start filling to the so pi star anti-bonding level. So that time what happened, this bond order becomes weaker. That means that as the bond order becomes weaker, so what, automatically the bond length will be increases. That is the same thing is happening here. When the back donation is happening from the metal atom, the d pi orbital into the ligand LUMO, so what happen, the C double bond C pi star anti level start filling up. At that time automatically, so these bond length will be increases because their bond order are like kata, so bond multiplicity will be decreases, so automatically the bond length will be increases. What I mentioned here, the pi, when the metal will be start giving back donation, so that will be the ability to form water, that pi bond here. So first is this is a sigma bond, whereas the bond back donation, so this metal atom is ability to form the pi bond. So that what happen, automatically when the pi bond is forming here, so this bond will become water, so sigma. So then what happen, increases. So the sigmas is carbon carbon double bond with the alkene lengthens and the bonding, that will be can be seen. The earlier should be like what, if you see this, so this bond length is smaller. When if you see this bond length will be so larger as compared to this one. M alkene sigma bond depletes carbon carbon pi bond by partially transferring these electrons to the metal, and so slightly weakens and therefore lengthens it. So when the electron density is moving towards the central metal atom, automatically what happens, the electron density on this bond will be decreases and the bond length will be increases. The major factor in the lengthening of carbon carbon double bond, however, the strength of the back donation from the metal. So whatever it may be, this pi bond is there. Once it is forming, so the bond with the central metal atom, because the donation of electron density from the ligand to metal atom takes place first. So that's why we can mention here the arrow mark here. This the electron density is taking place from here. Once it is formed, gain the electron density, it will become electron rich. So once it is start giving back electron density, giving back to the pi star orbital of the carbon carbon double bond group. So this back donation can be sharply lowers the carbon carbon bond order, so which is coordinating with the alkene. So this will be us, and whenever this electrons are going to start to fill the so anti bonding levels, so that anti electrons are entering to the anti bonding levels, so that can be automatically reduces the so bond length, because so always the electrons filling up electrons in the anti bonding level, which will be decreases the so bond order of the so slide. See, this C1, C2, C3, and C4. So, when back donation, automatically what happen? This bond become what a pi bond. Automatically, when it will be become pi bond, which is very sigma here, it is this bond is larger as compared to this one. So automatically what happen, as this back donation will happen, so this become pi bond and this become sigma bonds. As this become sigma bond, this will become larger as in size, and this bond become what a short, that is C1 and C2 is short lengthens, and C2 and C3 becomes so larger, so shorter, so because of what anti bonding. So then that was given here. So this is the HOMO levels and this is called LUMO levels, because on back donation the electrons are start filling to this one, so that automatically what bond length will be becomes decreases. This is the bonding system in the alkynes. Alkynes behave in a way broadly similar to alkenes, but being more electronegative, they tend to encourage back donation and bind more strongly. See, this is alkynes that will be having a triple bonds in the ligands here, here, and here, whereas tungsten is ability to form with the bonding with the all the ligands. The substituent tend to pull back away from the 30 to 40 degree in the complex, and the MC distance is slightly shorter than the so corresponding alkene complexes. The metallocyclopropene model seems often be the most appropriate description when the alkynes acts as a 2 electron. More interestingly, alkynes can form complexes that appear to be coordinatively unsaturated. See now here, when the central metal atom will be ability to form the bonding with the no, alkynes, So what happen automatically here also, these ligands are try to move away as possible, as much as possible. That is what we mentioned here, 30 to 40 degree. As these ligands are moving as much as possible, so which will be ability easy to make a bond with a central metal ion with this and this. So that what happen among these three bonds, so one bond is breaking, so this will be forming a two sigma bonds, so automatically what happened, this bond length will be increases, so that will be what happening in the so alkyne so this is a bonding system in the cyclobutadiene complexes. So this is cyclobutadiene complexes. The cyclobutadiene, the complexes are very stable and have been known for many years. But pre-dienes are so highly reactive that stable examples which are reported much later. The pre-molecule with 4 pi electrons is anti-aromatic and rectangular, because in the cyclobutadiene all are form of anti-aromatic, and it will be a rectangular form, but the ligand is square and seems to be aromatic. So it looks like aromatic, but it will be anti-aromatic. The metal must stabilize the diene by populating the LUMO for the pre-diene by back donation. So this, when the metal atom, similarly here, and the once a bonding will be forming with the central metal atom, that negative charge is accumulating on the central metal atom, and hence the central metal atom is start giving back the electron density to the central ligand. So those electron densities increases the populating the electron density and the LUMO level of the pre-diene and back donation. Automatically what happen, that bond length will be decreases. That will be given here. So ruthenium examples which are given. So that can be the Cl ligands are changing, replacing with that of the so carbonyl. So this is the bonding system in the arenes. Arenes, we all know that there are benzene ring systems. So here one benzene ring and here is one benzene. Two arene groups are there. But whereas see here it's one ring arene group and here other carbonyl group. Arenes usually bind transition metals in the 6 electron, that is representation eta 6 form. The carbon-carbon distance are usually essentially equal. So in generally here all the carbon-carbon bonds are usually equal, but slightly larger than the pre-arene. See example, the same benzene ring, if you consider it is, if it is pre, so the bond lengths are shorter, but when it is bonding with the central metal atom, automatically the bond lengths are so larger, that is mentioned here. So in the carbon-carbon distance are usually essentially equal, but slightly longer than the pre-arene. So that means that when if it is in the complex form, it will be the density is moving to the central metal atom, automatically the bond length will be increases. Arenes are much more reactive than the cyclopentyl compounds groups, and they are also more easily lost from the metal, so that arenes are normally actors rather than the spectacular and ligands. See now here, that is can be represented as eta 6 here, eta 6 here. So this is eta 1, eta 1, eta 1, and it is eta 6. So this is another type ligand. It is eta 7, and so there here examples that are taken, epta trienal compound. So this is epta ring. We will be having got 3 pi bonds here. So here also we can be seen that the formation of what are the complexes here given, complex are given, and here also chromium complex, and once it is forming a cation, and on reduction, and which is forming this complex, so which will be forming on reduction. So that is the explanation I given here. It will be similar to that of the previous things, and here it is eta 8 ligands, so it will be also form the similar kind of so ligands, whereas uranium I given here is in a metal atom. And finally this is another example with the titanium. So whereas eta 8, that is C8H8 complexes which are forming so with the different ligands. This is the bonding system is happening from what eta 1 to eta 8, or like what H1 to H8 complexes, so with the different bonding modes. As we all know that in almost all the ligands, so there will be possibility of formation of electron density in the from ligands to metal atom, and vice versa. The ligand is metal is start giving back the electron density to central atom, automatically the bond length will be decreases. Okay, so in my next presentation I will give you with some examples, there you clearly understand. So that will be with the reactions. So thank you.